Good morning. My name is Alex Gonzalez, and I've done this work at CSU with, in collaboration with my advisor, Wayne Schubert, and former student Gabriella, and also research scientist Richard Taft. And this work has been supported by CMAP, which is an NSF Science and Technology Center. So a little bit of background here on deep and shallow circulations. Traditionally, the Hadley circulation is considered it's a zonally symmetric overturning circulation, which is driven by diabatic heating in the ITCZ. Now, more recently, there has been observational evidence of a shallow overturning circulation. And in the schematic below, we have both the deep and the shallow Hadley circulation and the convection in the ITCZ. In order to understand this, from a theoretical point of view, we formulate an idealized model, an equatorial beta plane model, to gain insight into the dynamics of both circulations. So this is based off some work which was just published, Balanced Dynamics of Deep and Shallow Hadley Circulations. So these are the model equations. We've got 5 equations, and they're linearized on the equatorial beta plane. And we have 5 equations, 5 unknown variables, and so we actually have 6 variables here, and so we prescribe the diabatic heating, which is Q over Cp in the last equation. And this is the vertical coordinate here is a log pressure coordinate. And we have hydrostatic balance for the first model. Since it's talking about balance dynamics, we also make an assumption here of balanced flow in the meridional momentum equation, and therefore we have geostrophic balance there. And the equation that you can get from this, you can form a stream function. You can put together a stream function. Since it's zonally symmetric, you're only working with 2D dynamics. And so you come up with this transverse circulation equation for psi, which is a stream function. And this equation is described by 2 shaping parameters: the inertial stability, which is given here, and the static stability. The inertial stability is resistance to horizontal motion, and the static stability is your resistance to vertical motion. And on the right-hand side, you have your diabatic heating, which is prescribed. And the boundary conditions are pretty straightforward for equatorial beta plane dynamics. The stream function goes to 0 as you go away from the equator, and then also the stream function is 0 at the top of the fluid layer, and then at the bottom, this is actually a model for the inviscid interior, so it doesn't include boundary layer dynamics. So z equals 0 is actually the top of the boundary layer, and so that's why it looks a little complicated, but it basically allows for you to prescribe a vertical velocity at the top of the boundary layer, and that's the Ekman pumping that we're going to prescribe, and you get the shallow Hadley circulation out of that. So here are basically the main points here for this balanced Hadley circulation paper, and the 4 panels describe 4 displacements of the ITCZ. The first one is closest to the equator, and as you go down, you get further and further away from the equator. The left panel just shows from 0 to 13 kilometers above the boundary layer, whereas the right panel shows 0 to 3 kilometers above the boundary layer. So the scales are slightly different. And the 0 line is the equator. So you have rising motion on the left-hand side. On the left panels, you have the deep Hadley circulation, where you have rising motion in the ITCZ and subsidence away from the ITCZ. And in the right panels, you have this divergence associated with the Ekman pumping being shot out because of the resistance to horizontal motion is much smaller near the equator than the resistance to vertical motion because the inertial stability goes to 0 at the equator. And so this winter cell, as you keep going down on the panels, becomes more and more dominant, and there's a larger asymmetry. And this is well observed between the winter and the summer cell. And this is described mostly by that inertial stability parameter, which makes sense because it shows up in the equations as a shaping parameter. And so now we look at the transient aspects of the Hadley circulation. And we're really going to focus mostly on the deep Hadley circulation here. A lot of the same ideas applied to the shallow Hadley circulation. It's just the forcing is different. It's boundary layer dynamics instead of the inviscid interior ITCZ forcing. Diabatic heating. So now we prescribe a transient diabatic heating that has memory, and we're going to see later what that means. It remembers how it was switched on, how the diabatic heating changed with time long before. So it has that sort of memory to gain insight into temporal variability of the deep Hadley circulation. And so there's been theoretical and observational evidence of equatorially trapped inertial gravity waves in the ocean a long time ago. Blandford in 1966 in his seminal paper on equatorial wave theory, and then Wunsch and Gill in 1976. So in the bottom left panel, I'm just showing just water vapor imagery of the winter and summer cell. So you can see that large asymmetry. And obviously there's transient dynamics that's happening there that we're going to speak about. And on the right panel, we have the sea level as a function of frequency on the x-axis, and on the y-axis we have energy density. And so the sea level at Canton shows a few peaks, but there's this one noticeable peak which they attribute to these equatorially trapped inertial gravity waves. And so we're extending this work to think about it in terms of the Hadley circulation. So same equations that we used before, but now we're going to include dV/dt, which allows for these transient inertial gravity waves. So it's no longer geostrophically balanced. And so the equations are the same, except now you have these time derivatives. They're second time derivatives, and therefore now we need to impose two initial conditions, and they're straightforward. The stream function is 0 and its derivative are 0 at time equals 0. And we're just going to be looking at the deep Hadley circulation, so the diabatic heating, we're just going to look at that as the forcing and not the Ekman pumping. So taking a look at some observations, well, reanalysis actually, I shouldn't call them observations. Yahtzee, Q1 over CP over Central and Eastern Pacific, and basically in the mid-levels did an average and one-day running mean. So there's a lot of variability here, of course, but a few particular time periods I want to focus on. This is what we would call sort of a slow switch on. The diabatic heating is going from one state to another state, but over the period of a few days, and then we've got a number of these really fast transitions. And so we're gonna, right now, since I only have so much time, I'm gonna look at really the fast switch on because that's where you get the most inertial gravity wave activity. And the function that we're using, the idealized function that we're gonna use, has 4 different switch on speeds. And we're gonna look at the fastest one, like I said, gamma to the -1 equals 3 hours, which is in the black line. And so we're gonna look only at that case, which the ITCZ is displaced basically between 10 and 15 north. So this would essentially be the largest asymmetry in that balanced case. So we will see lots of asymmetries, but this is basically supposed to show sort of the summertime, what is observed in the summertime as a sort of displacement of the ITCZ. So we have, this is going to be an animation here, so we have once again, the x-axis is the meridional direction where 0 is the equator, and then the y-axis is the vertical log pressure coordinate above the boundary layer. And so as we start this animation, the forcing gets switched on, and the winter cell becomes very dominant, so much so that the summer cell is almost gone. You can see this activity, you can see signals propagating away from the ITCZ and then back towards the ITCZ, hence some sort of trapping mechanism you have here. The solutions go from oscillatory to evanescent in the equatorial beta plane model. And so when they go to evanescent, when they stop being oscillatory, there's critical latitudes which trap these gravity waves and obviously change the Hadley circulation significantly. Of course, this is just a theoretical model, but this is interesting nonetheless. So in sort of wrapping up what you see in that animation, we have the ITCZ located between 10 and 15 north. We had this fast diabatic switch on, and the top panel shows the total stream function, which is just the sum between the summer cell and the winter cell, and it's normalized. So this basically is showing it's pretty erratic. You switch on the diabatic heating, and then you get a lot of oscillations, but in general, what you want to know here is that there's a memory of how the forcing was switched on initially, so it remembers how fast that happened. So the gravity wave activity then is trapped, and in the bottom panel, it shows a fractional mass flux between the winter and the summer cell. And then you have the dashed lines, which are basically the balanced solutions, which don't change in time, obviously. And so you have these trapped inertial gravity wave oscillations with somewhat of an irregular period, and I attribute that mainly due to the ITCZ. It has these it's displaced off the equator, so the summer cell is closer to the critical latitudes than the winter cell. So you get bouncing, but it's not like these gravity waves are hitting that critical latitude, those critical latitudes at the same time. So you get somewhat of an irregularity, but on the order of 40 to 60 hours of a period. And obviously you have these huge asymmetries for this case. And if we didn't really show the animation for the slow switch on, but this is the slowest of the 4 that I showed. And so this is the same ITCZ displacement, and then you switch it on slowly, and you obviously see in the top panel that there are less oscillations, and it looks more or less like the initial forcing that was turned on. There's not much gravity wave activity. And so there is memory of how that forcing was switched on, and the trapped inertia gravity waves in the bottom panel show that there are oscillations, but they oscillate. The oscillations are not too far away from the balanced results, and the asymmetries are close to the balanced solution. So there are a lot of possibilities here for how the atmosphere really would oscillate in response to the diabatic forcing. So in summary, we formulated an idealized model to gain insight into deep and shallow Hadley circulations for balanced and transient flows. The transient flows, we looked more at the deep here. And the balanced Hadley circulations, both the deep and the shallow, have an asymmetry. And this is between the winter and summer cells when the ITCZ is off the equator, and this is due to the inertial stability parameter, which is the only varying parameter, and it varies with latitude or meridional distance. And then when we looked at the transient dynamics, the deep diabatic heating, when it's switched on fast, the deep Hadley circulation is really dependent on time, and a spectrum of trapped inertia gravity waves travels in rays away from the ITCZ and bounces off these turning latitudes, which I didn't get a chance to really go into the theory behind that, but there's a lot of theory behind that. The different meridional modes have different turning latitudes and so forth. And we have these wave packets moving the information. Since the summer cell is closer to these turning latitudes, the period of ringing can be irregular, and especially for the fast switch on. But in general, we had a period of somewhere around 40 to 60 hours for all the switch ons, which I didn't show. And then now the next steps, I want to look at observations to see, it'd be nice to look at upper level observations or observations above the boundary layer to see if these sort of fluctuations in particular fields like the wind fields show up. And then relax the assumption of zonal symmetry in an idealized model forced by localized transient diabatic heating, which I'm working on right now. Thank you. Well, you have to sort of include, so if you want to do something like that, that was essentially the slow switch on. If you just were to switch on the diabatic heating very slowly, which is what I showed in the last, sort of the last. Mm-hmm. Mm-hmm. Yeah, it's just, there's just one term that was neglected between the two. There's one different term. Mm-hmm. Yes. So the idea there is that there is time evolution of the zonal flow, but it's constantly in geostrophic balance. But there is no transient. There's no memory of the Hadley circulation. It's steady in that case. Yes, yeah. Maybe we can talk about it more after. Thanks.